We are now on the third chapter of Mechanics 107, and on this chapter, we will tackle about torsion. Here, we will consider the derivation and application of the twisting or torsion problem in circular shafts or closed thin wall tubes. So, torsion is the twisting of an object due to an applied torque, and a torque is a moment that twists a structure or a material. So unlike axial loads that produces uniform or average stress over the cross-section of the object, a torque creates a distribution of stress over the cross-section. And it's often applied on rods and shafts. And to be able to understand or to figure out what is torsion or what is torque all about, let us consider a bar that is rigidly attached at one end. So if there is no force applied on the rod, it stays the same. But if we try to apply a force multiplied by the distance, or what we call the torque or twisting moment, that is being applied perpendicularly to the axis of the bar, an angle of twist is being created. So, mapapansin nyo dito, if we twist the rod, magkakaroon ng angle of rotation or angle of twist. For a solid or hollow circular shaft subject to a twisting moment, the torsional shearing stress at a distance rho from the center of the shaft is represented by this formula. So the maximum shearing stress would now be equal to the torque multiplied by the radius divided by the polar moment of inertia. So torque is also the twisting moment. And we have different formula in order to arrive for the polar moment of inertia. For cylindrical shaft or for solid cylindrical shaft, the polar moment of inertia is equal to pi all over 32 multiplied by the diameter raised to 4, and the shearing stress or the maximum shearing stress is equal to 16 multiplied by the torque divided by pi d raised to 3. So if I will draw a solid shaft, ito yung di na tinutukoy, the outside diameter. And for the hollow cylindrical shaft, this would be the outside diameter, and this would be the inner diameter, in which our polar moment of inertia would now be equal to pi all over 32 multiplied by the outer diameter raised to 4 minus the inner diameter raised to 4, and then the maximum shearing stress is equal to 16 multiplied by the torque or the twisting moment multiplied by the outside diameter divided by pi d raised to 4 minus the inner diameter raised to 4. As I have said earlier, if we apply a force on the rod, it will create an angle of twist, and it can be solved through this equation, in which the angle of twist is equal to the torque multiplied by the length divided by the polar moment of inertia multiplied by the shear modulus of that material. And the power transmitted by the shaft can be derived using this formula, in which our P is equal to power expressed in watts. It is equal to the torque multiplied by the rod per unit time, or can be derived using this formula, the product of 2 pi multiplied by the torque multiplied by the number of revolutions per second. So if the shaft is rotating with a frequency of f revolution per unit of time, we can say that omega is equal to 2 pi multiplied by the frequency of revolution f. So in order to understand better, let us solve problems. What is the minimum diameter of a solid steel shaft that will not twist through more than 3 degrees in a 6 meter length when subjected to a torque of 12 kN that meter. What maximum shearing stress is developed? So we will use the shear modulus of elasticity as 83 gigapascal. So the given, the angle of twist is equal to 3 degrees. The length is 6 meters. The torque is 12 kN that meter. And the shear modulus is equal to 83 gigapascal. So let us convert first lahat ng to in terms of Newton and in millimeter. And it is very important to take note that the angle of twist must be in rad. So multiply natin siya ng pi all over 180. So it is equal to pi over 60. And then our length is 6,000 millimeters. And then the torque is equal to 12 times 1,000 squared Newton that millimeter. And then 83 gigapascal is equal to 83,000 megapascal or Newton per square millimeter. And for this solid steel shaft, the polar moment of inertia is equal to pi all over 32 d raised to 4. So, ang hinahanap natin first is the minimum diameter. So, the angle of twist is equal to the torque multiplied by the length all over the polar moment of inertia multiplied by the shear modulus. So, substitute lang natin yung mga given. So, pi all over 60 is equal to the torque, which is 12 times 1,000 squared. The length is 6,000 millimeters. Polar moment of inertia. So, let us ilagay muna natin as polar moment of inertia and then multiplied by 83,000. Therefore, the polar moment of inertia is equal to So it is equal to 1656745.32 millimeter raised to 4. And then the polar moment of inertia is expressed by this formula. So substitute lang natin yung polar moment of inertia with this. Therefore, the diameter would now be equal to the fourth root of 1656745.32 all over pi divided by 32. Therefore, the diameter is equal to 113.98 millimeters. So, this would be the minimum diameter of the solid shaft. And then, hinahanap rin ng problem yung maximum shearing stress that is being developed. So, our maximum shearing stress for solid steel shaft is equal to 16 multiplied by the torque divided by pi d raised to 3. So, substitute lang natin 16 and then the torque is 12 times 1,000 squared all over pi. And then the diameter is 113.98 millimeters. So the maximum shearing stress would now be equal to So it is equal to 41.27 Newton per square millimeter or 41.27 megapascal. So ito yung hinahanap ng problem. For the next problem, A steel shaft 1 meter long that has a diameter of 100 millimeter is subjected to a torque of 20 kilonewton meter. Determine the maximum shearing stress and the angle of twist. The shear modulus is equal to 83 gigapascal. So the diameter is 100 millimeter. The torque is 20 kilonewton that meter. So we will determine the maximum shearing stress and the angle of twist if our shear modulus is equal to 83 gigapascal. Our formula for the maximum shearing stress is equal to 16 multiplied by torque divided by pi d cube. So substitute lang natin 16, which is 20 times 1000 squared newton that millimeter, pi, and then the diameter is 100 millimeter raised to 3. So the maximum shearing stress is equal to 101.86 megapascal. And the angle of twist is equal to the torque multiplied by the length all over the polar moment of inertia multiplied by the shear modulus of elasticity. So, torque natin is 20 times 1000 squared. The length is 1 meter long, so 1000 millimeter. Polar moment of inertia is pi all over 32. The diameter is 100 raised to 4 and then multiplied by 83,000. So it is equal to, so ang lalabas sa sagot dito is expressed in rad. So it is 0.0245 rad. 0.0245 rad. So if we want to convert it in degree, multiply lang natin siya ng 180 degrees all over pi. So it is equal to 1.4 degrees. So the angle of twist is equal to 1.4 degrees. So ito yung hinahanap ng problem, the angle of twist, and then the maximum shear stress, which is 101.86. A steel marine propeller shaft 355 mm in diameter and 5.5 meter long is used to transmit 3,730 kilowatts at 3.15 revolution per second. If the shear modulus is equal to 83 gigapascal, determine the maximum shearing stress. So our propeller has a power of 3,730 kilowatts. So convert natin siya into watts by multiplying 1,000. So magiging 3,730 times 10 raised to 3 watts. And we know that watts is equal to joule per second. And joule is equal to newton that meter. So the power would now be equal to 3,730 times 10 raised to 3 newton that meter per second. But I want to use a millimeter on this part, so multiply lang natin siya ng 1,000. So magiging 3.73 times 10 raised to 9 newton that millimeter per second. Para uniform lahat, newton and in millimeter. And then our frequency is equal to 3.15 revolution per second. The shear modulus is equal to 83,000 megapascal or 83,000 newton per square millimeter. the length is equal to 5.5 meters or 5,500 millimeters. And then the diameter is equal to 355 millimeter. So I have introduced to you a while back that the formula for power transmitted by the shaft is equal to 2 pi multiplied by torque multiplied by the frequency. So substituting the given on this formula, so magiging 3.73 times 10 raised to 9 is equal to 2 pi. Yung hinahanap natin na torque multiplied by the frequency, which is 3.15. So the torque would now be equal to 188.46 times 10 raised to 6 Newton that millimeter. And then the maximum shearing stress is equal to 16 multiplied by the torque divided by pi d raised to 3. So substitute lang natin. So 16 multiplied by 188.46 times 10 raised to 6 Newton that millimeter all over pi. Yung diameter natin is 355 raised to 3 millimeter raised to 3. So cancel. The shearing stress would now be equal to 21.45 Newton per square millimeter or 21.45 megapascal. So, ito yung hinahanap ng problem. A steel propeller shaft is to transmit 4.5 megawatts at 3 Hz without exceeding a shearing stress of 50 megapascal or twisting through more than 1 degree in a length of 26 diameters. Compute the proper diameter if the shear modulus is equal to 83 gigapascal. So the power that is being transmitted is equal to 4.5 megawatts or equal to 4.5 times 10 raised to 6 watts or 4.5 times 10 raised to 6 Newton that meter per second. So, multiply lang natin siya ng 1,000 para Newton that millimeter per second yung kakalabasan niya. So, magiging 4.5 times 10 raised to 9 Newton that millimeter per second. So, that's the power. And then, Hertz is equal to revolution per second. So, our 3 Hertz, yung frequency natin na 3 Hertz, is just equal to 3 revolution per second. And the shearing stress is equal to 50 megapascal. And then our angle of twist is 1 degree in a length of 26 diameters. So we will compute the proper diameter if the shear modulus is equal to 83,000 megapascal or 83,000 Newton per square millimeter. Our formula is equal to 2 pi f, in which our power natin is 4.5 times 10 raised to 9 is equal to 2 pi. The frequency is 3 Hz or 3 revolution per second. And then, hinahanap natin is yung torque. So, the torque would now be equal to 238.73 times 10 raised to 6 Newton dot millimeter. And then our maximum shearing stress is equal to 16 P all over pi d cube. So 16 multiplied by 238.73 times 10 raised to 6. Ang shearing stress natin is 50 megapascal or 50 newton per square millimeter. So the diameter is equal to 289.71 millimeter. And also, considering the angle of twist, which is equal to torque multiplied by the length all over the polar moment of inertia multiplied by the shear modulus of elasticity, in which yung ating angle of twist is equal to 1 degree in a length of 26 diameters. So it will be equal to, so as I have said earlier, dapat nakarad yung ating angle of twist. So multiplied by pi all over 180. And then 238.73 times 10 raised to 6. Our length is equal to 2060. So a length of 26 diameter. So 26 multiplied by the diameter daw. And then the polar moment of inertia, pi all over 32, d raised to 4. And then the shear modulus is 83,000. So cancel that out, magiging 3 to. So the diameter is equal to, further simplification, so the diameter is equal to 352.08 millimeters. So we will consider the bigger diameter, which is 352.08. So ito yung final answer. Next problem. An aluminum shaft with a constant diameter of 50 mm is loaded by torques applied to gears attached to it as shown. Using shear modulus of 28 gigapascal, determine the relative angle of twist of gear D relative to gear A. So let us determine first the moment that is acting on each rod, or acting between each rod. So I will pass imaginary lines between each gear. So for the first imaginary line, there is a torque acting between C and D. So pangalanan natin siya as torque between D and C. So summation of moment is equal to 0. Is equal to 800 Newton that meter. And for the imaginary line B, same procedure. So yung gear C natin has 1,100 Newton that meter. And yung gear D natin has 800 Newton that meter. So it has a torque here between rod, or between gear B and C. So summation of moment is equal to 0. So 800 minus 1100 plus the torque between C and B. So this must be C and B is equal to 0. Therefore, it is equal to 300 Newton that meter. And for the last part, so yung gear B natin has a 900 Newton millimeter. Or 900 Newton that meter. So summation of moment is equal to 0. So 800 minus 1100 plus 900 minus the torque between B and A is equal to 0. Therefore, it is equal to 600 Newton that meter. So the problem is asking for the relative angle of twist of gear D relative to gear A. So the angle of twist relative to D and A. So it is equal to TL all over JG. So it will be equal to 800. That is in Newton that meter. So convert lang natin into Newton that millimeter by multiplying it with 1000 para maging Newton that millimeter. And then the length is 2 meters or 2000 millimeters. And the polar moment of inertia is pi all over 32. The diameter is 50 millimeter as stated in the problem, raised to 4. And then the shear modulus is 28,000 megapascal. Minus. So, bakit minus? Makikita niyo yung orientation ng ating mga arrow. And then plus 600 Newton that meter. And then the length is 2000 millimeters all over pi 32 multiplied by 50 raised to 4 of 28,000. Therefore, the angle of twist relative to gear D with A or relative to gear A is equal to, so the answer is in rad. So convert natin mamaya into degrees by multiplying it by 180 divided by pi. So it is equal to 0.111 rad. So multiply lang natin siya into 180 divided by pi. So it is equal to 6.34 degrees. So the answer is 6.34 degrees. The relative angle of twist of gear D relative to gear A is 6.34 degrees. A compound shaft consisting of a steel segment and an aluminum segment is acted upon by two torques as shown. Determine the maximum permissible value of T subject to the following conditions. The shear stress for steel is 83 megapascal, the aluminum is 55 megapascal, and the angle of rotation of the free end is limited to 6 degrees. For steel, the shear modulus is equal to 83 gigapascal and the aluminum is 28 gigapascal. So again, we will pass imaginary lines here para makita natin yung mga torque na nag-a-act between each rod. So at this part, there is a torque. So let's say this is TA. Summation of moment is equal to 0. So T is equal to our TA. And for our second imaginary line, so let's say this is TA or TS, I should say. So summation of moment is equal to 0. So magiging negative T minus 2T plus TS is equal to 0. Therefore, TS is equal to 3T. And we have our formula for maximum shearing stress, which is equal to 16 multiplied by the torque divided by pi d raised to 3. So, unahin natin yung aluminum. So, the shear stress for aluminum is 55 megapascal. So, 55 Newton per square millimeter. 16, the value of T for aluminum is equal to T all over pi, and then the diameter is 40 millimeter. Therefore, T is equal to 691,150.38 Newton that millimeter. And then for steel, so ito is yung aluminum kanina. And then let us proceed to steel. The shear stress is 83 megapascal, 16, and then the value of T is for steel 3T divided by pi multiplied by the diameter, which is 50 raised to 3. Therefore, T is equal to 679,042.16 Newton that millimeter. And also, an angle of twist is given, which is equal to 6 degrees as the angle of rotation. So, di ba yung angle of twist natin is equal to TL all over JG. So, 6 degrees multiplied by pi all over 180. So, convert sa rad. And then T multiplied by the length. Yung length natin is 600 for the aluminum. And then pi all over 32. The diameter is 40 raised to 4. And then the shear modulus is 28,000 plus yung T natin for steel, which is 3T. Tama, 3T multiplied by 900 as the length all over pi 32. Yung diameter niya is 50 raised to 4, and then shear modulus is 83,000. Therefore, T is equal to, solving simultaneously, our T is equal to 757,316.32 Newton that millimeter. Therefore, we will be considering the least torque, yung pinakamababang value that the compound shaft can carry, which is 679,042.16 Newton that meter. Therefore, we will consider 679,042.16 Newton that millimeter as the safest torque it can carry. So this would be the final answer. So next is the flange bolt coupling. Flange bolt coupling is another sort of connector between two arrangements of flanges, and the flanges are fitted or provided at the end of the shafts. The flanges are tightened together by means of number of nuts and bolts. So the torque is transmitted by the shearing force P created in the bolts and is assumed to be uniformly distributed. For any number of bolts, and the torque capacity of the coupling is given by this formula, in which the torque is equal to the force that acts to the center of the bolt and also tangent to the bolt circle multiplied by the radius of the bolt circle multiplied by the number of bolts. So, i-drawing natin yan, parang ganito. So, these are the bolts na naka-attach sa ating flange. So, the P is acting on the center of the bolt. And if I will draw an imaginary line here, it is acting tangent to the bolt circle. So, ito yung tinatawag na bolt circle. So, this is P that is acting on the center of the bolt and is tangent to the bolt circle. In which yung ating P, kung mapapansin nyo, is the product of the shear stress multiplied by the area of the bolt. Kaya naging pi d squared over 4, which is the area ng ating bolt multiplied by the shear stress multiplied by R and the number of bolts. So if a coupling has two concentric rows of bolts, the torque capacity is given by this formula. So we have two rows ng bolts. We have the outer diameter of bolt circle and an inner diameter ng bolt circle, which is signifies a 2. And then yung outer is yung subscript natin na 1. So for the outer, yung force natin is also acting on the center of the bolt. And then it's tangent to the bolt circle. And then ito yung radius niya from the center. And then for the inner circle naman, we have here the force acting on the center of the bolt also. And it's tangent to the inner bolt circle. So this is the formula. So for rigid flanges, the shear deformations in the bolts are proportional to the radial distances from the shaft axis. Therefore, the shearing strains are related or represented by this formula. And then using Hooke's law for shear, in which our shear modulus is equal to the shear stress all over the strain. So, ito yung magiging formula niya. Substitution lang. And then, if the bolts on the two circles have the same area, A1 is equal to A2, and if the bolts are made of the same material, the relationship between P1 and P2 is represented by this formula. So, this is only applicable if the flanges or the bolts on the circles have the same area and the bolts are made with the same material. So, for our examples, let us proceed to our example number 1. Problem number 1. A flange bolt coupling consists of 10 20 mm diameter bolts spaced evenly around a bolt circle 400 mm in diameter. Determine the torque capacity of the coupling if the allowable shearing stress in the bolts is 40 megapascal. So if I will try to draw the scenario, we have a flanged bolt coupling, and it is being fastened by 10 pieces of 20 millimeter diameter bolts that is spaced evenly. So we have 10 pieces of 20 millimeter. So let's say 1, 2. So let us assume that it is spaced evenly. So the bolt diameter is, or the bolt circle is 400 millimeter in diameter. We will determine the torque capacity of the coupling if the shearing stress is 40 megapascal. So our formula here, the torque is equal to the force multiplied by the radius of the bolt circle multiplied by the number of bolts, in which the force is equal to shear multiplied by the bolt diameter. So yung shearing stress natin is 40 megapascal or 40 newton per square millimeter, and then the area is pi all over 4. Yung bolt diameter natin is 20 millimeter, so 20 squared. Therefore, P is equal to 12,566.37 Newton. So substituting the given formulas to the equation. So T is equal to 12,566.37 Newton, and then the radius of the bolt circle is 200 millimeter, and then the number of bolts is 10 pieces. Therefore, the torque capacity is equal to 25.13 times 10 raised to 6 Newton that millimeter, or 25.13 kilonewton that meter. So this is the final answer. Next, a flange bolt coupling consists of 8 10mm steel bolts on a bolt circle 400 mm in diameter and 6 10mm diameter steel bolts on a concentric bolt circle 300 mm in diameter is shown. What torque can be applied without exceeding a shearing stress of 60 megapascal in the bolts? So at the outside bolt circle, we have 8 pieces of 10mm steel bolts, and the inner bolt circle has 6 pieces of 10mm steel bolts. So P1 is equal to the shear multiplied by the area 1. So ang shear natin is 60 megapascal, and then the area 1, or the area of the bolt at the outer bolt circle, is pi all over 4. Yung diameter na dyan is 10mm. So it is equal to 4,712 Newton. 0.39 Newton. And for inner, so let's say this is for outer, and for inner bolt circle, using ratio and proportion, then the R1 is 200, and then the R2 is 150 millimeters. Therefore, P2 is equal to 3,534.29 Newton. And the problem is asking for the torque that can be applied without exceeding the shearing stress. So the torque is equal to for the outside circle, so for the outside circle diameter, so 4712.39 multiplied by 200, so this is 8 pieces, plus for the inner 3534.29 multiplied by 150 multiplied by 6 pieces. Therefore, it is equal to equal to 10.72 times 10 raised to 6 Newton dot millimeter, or 10.72 kilonewton dot meter. So this is the final answer. Next problem. A torque of 700 pounds-feet is to be carried by a flange bolt coupling that consists of 8 1/2 inch diameter steel bolts on a circle of diameter 12 inch and 6 pieces of 1/2 inch diameter steel bolts on a circle of diameter 9 inch. Determine the shearing stress in the bolt. So for the outer, we have 8 pieces, and the diameter is 1/2 inch diameter, and for the circle of bolt, it is 12 inches diameter, so it is equal to 6 inches in radius. And for inner, it has 6 pieces of 1/2 inch diameter steel bolts on a circle of diameter of 9 inches or radius of 4.5 inches. So we will determine the shearing stress in the bolt. So first, determine muna natin yung torque. Torque is equal to P1 R1 N1 plus P2 R2 N2. So the torque is 700 pounds-feet, so 700 pounds-feet. And I would like to convert this into inches para uniform lahat. So multiply lang natin siya by 12 inches. Is equal to P1. Yung R1 natin is 6 inches. And then 8 pieces. Plus P2. R2 natin is 4.5 inches with 6 pieces of bolt. Therefore, is convert natin yung P1 in terms of P2. So it is 8,400 divided by, so this is 48. Divided by 48 minus 4.5 multiplied by 6 is 27. All over 48 of P2 is equal to P1. So this would be our equation number 1. For equation number 2, through ratio and proportion, P1 R1 is equal to P2 R2. So our P1, yung R2 natin is 4.5. And then P2, yung R1 natin is 6. Therefore, P1 is equal to 6 divided by 4.5, which is 1.33 of P2. So we have equation 2. So solving simultaneously using equation 1 and equation 2, equate lang natin. So 8,400 all over 48 minus 27 all over 48 of P2 is equal to 1.33 of P2. Therefore, P2 is equal to 1.33 92.47 pounds. Therefore, our P1 is 122.98 pounds. So the problem is asking for the shearing stress in the bolt. So using the equation, talagyan natin dito, of P all over A. So for our shear 1, our P is 122.98 pounds, and then the area is pi all over 4 of 1/2 inch squared. So it is equal to 626.33 pounds per inches squared. 0.33 pounds per inches squared, or PSI. And for our shear 2, P2 all over A2. So yung P2 natin is 92.47 pounds divided by the area, which is pi all over 4 of 1/2 squared. So it is equal to 470.08 pounds per inches squared. 470.95, I should say, PSI. So this is, or these are the final answers. So for the bolt in the outer diameter is equal to 626.33 PSI, and for the inner bolt diameter, it is equal to 470.95 PSI. Next, a plate is fastened to a fixed member by 4 20mm diameter rivets arranged as shown. Compute the maximum and minimum shearing stress developed. So we have here a plate that is fastened by 4 pieces of 20mm diameter. So let us locate the center of gravity. So yung center of gravity is located at this point. In which our shear stress is equal to the torque multiplied by rho divided by the polar moment of inertia. In which our torque is equal to 14 kilonewton, 14 times 10 raised to 3 newton, multiplied by the distance, which is, so kung 80 to, so half of this is 40, and then 80, so it is equal to 120 millimeters. So the torque is equal to 1.68 times 10 raised to 6 Newton that millimeter. And then yung polar moment of inertia natin, which is J, is equal to the summation of the area multiplied by the rho squared, in which rho squared is the distance of the bolt to the center of gravity. Area 1 natin is pi all over 4 20 squared. So dito muna tayo mag-focus at this bolt. Rho is the distance to the center of gravity, which is 120 squared. And the next one, dito sa bolt na to, plus pi all over 4 of 20 squared, and then 40 squared. Next, this one, and next is this one. So plus pi all over 4 of 20 squared, rho is 40 squared, plus pi all over 4 of 20 squared of 120 squared. Therefore, the polar moment of inertia is equal to This is equal to 10.05 times 10 raised to 6 millimeter raised to 4. And the problem is looking for the maximum and the minimum shearing stress that is being developed. So the maximum shearing stress is developed or located at this part, and the minimum shearing stress is developed at this part. So for maximum shearing stress, 1.68 times 10 raised to 6 Newton net millimeter. Rho is 120 millimeter all over the polar moment of inertia, which is 10.05 times 10 raised to 6. So it is equal to 20.06 Newton per square millimeter or megapascal, and then the minimum shearing stress is equal to 6.69 Newton per square millimeter. So this is the minimum shearing stress, 6.69 megapascal, and the maximum shearing stress is 20.06 megapascal. So these are the final answers. Next is for the torsion of the thin-walled tubes. So the formulas that we will encounter here are just simple approximation that are available for thin-walled tubes. And such members are common in construction where lightweight is of paramount importance. So here we will consider, or we will assume that the tube are in prismatic, or let's say constant in cross section, but the wall thickness is allowed to vary within the cross section. So we will consider a tube that is rigidly attached to a wall, and let's say, or let us assume that the cross section is constant. So let us assume that the cross section is constant up to the end, but the wall thickness is allowed to vary within the cross section. So this is represented as the length, and then torque is being applied on the axis, and it has a certain thickness T. And the torque applied to thin-walled tube is expressed by this formula. So our torque is equal to 2 multiplied by the cross-sectional area, or the area enclosed by the center line of the tubes, multiplied by the shear flow. So the A here, or the area enclosed by the center line of the tubes, is represented, or let us begin here. So ito yung sinasabi niya na cross-sectional area that is enclosed by the center line of the tubes. So center line of the tubes, so ito yung consider natin na area. And then the average shearing stress across any thickness T is represented by this formula, in which our shear stress is equal to the shear flow divided by the thickness. And then using this formula, shear flow is equal to torque divided by 2 multiplied by the area. So kung i-substitute lang natin dito, magiging ganito yung itsura ng ating shear stress. So ito na yung ating Q, shear flow. So the torque can also be expressed as 2 multiplied the cross-sectional area that is enclosed by the center line of the tube, multiplied by the thickness, multiplied by the shear stress. So to further understand, let us proceed to our first example. A tube 2.5 mm thick has an elliptical shape as shown. What torque will cause a shearing stress of 56 megapascal? we will be looking for the torque, in which the shearing stress is equal to 56 megapascal. So our formula is equal to 2 multiplied by the area multiplied by the thickness and then the shearing stress. So 2, the area of an elliptical shape is equal to pi of the radius 1 multiplied by the radius 2. So ito yung magiging R1 natin. And this would be our R2. R1 natin is 75 all over 2. And then yung R2 is 150 all over 2. The thickness is 2.5 millimeters. And then the shearing stress is 56 megapascal. So our torque is equal to, so it's very easy, direct substitution only. So it is equal to 2.47 times 10 raised to 6 Newton that millimeter, or if you want it to convert in kilonewton that meter, it is equal to 2.47 kilonewton that meter. So this is the final answer. Next, a torque of 450 pounds-feet is applied to the square section. Determine the smallest permissible dimension A if the shearing stress is limited to 6,000 psi. So again, our formula for torque is equal to 2 multiplied by the area multiplied by the thickness and then the shearing stress. So our torque is equal to 450 pounds-feet, but I want to use pounds inches para uniform lahat. So multiplied lang natin by 12 inches. So it is equal to 5,400 pounds, feet, yes, pounds that inches. And then our shearing stress is 6,000 psi. So we are looking for the permissible dimension A. So 5,400. So substitute lang natin yung mga values at this point. The area for square is a square, of course. And the thickness is 0.1 inch. And then the shearing stress is 6,000. Therefore, A is equal to square root of 5,400 all over 2 times 0.1 times 6,000. So it's equal to 2.12 inches. So this would be the final answer.